Hello everyone, my name is Leyang Hu, and today I'm going to present the paper named Neural Tangent Kernel, Convergence and Generalization in Neural Networks. Here is the outline for today's presentation. So first, I will talk about the background and motivation for the paper, then the contribution. After that, I will go through the notation and terminology, and then the convergence analysis of the neural network. After that is the generalization analysis of the neural network under the specific setting of least square regression problem. So here's the background and motivation. We all know that artificial neural networks are black boxes. So the convergence and generalization properties of them are still largely unknown. There are many mysteries around these properties. For example, for a mystery around non-convex optimization, the neural networks have highly non-convex loss services. How do we know where will them converge to after the optimization process? And another mystery around generalization is the over-parameterization paradox. So an over-parameterized ANNs can fit random labels perfectly, but at the same time, it can also achieve a good performance on real data, on good test accuracy on real data. So how can they generalize well despite the risk of overfitting? The authors of the paper propose a new tool called the Neural Tangent Kernel to study the convergence and generalization properties of ANNs. So here are the contributions. First, the authors showed that when you're doing gradient descent in the parameter space, it is actually equivalent to doing the kernel gradient descent with respect to the so-called neural tangent kernel in function space. And the second contribution is that they prove the convergence of infinitely wide neural network training by leveraging the positive definite property of the neural tangent kernel. And thirdly, they demonstrate the why the neural networks might generalize well in the setting of linear regression, least square regression problems from the perspective of the neural tangent kernel. So before diving into the convergence analysis and generalization analysis, I would like to first go through the notation and terminology. Bear with me, this is going to be a bit tedious, but we need this for the later analysis. So in the article, the ANNs the authors consider have L+1 layers, where the zeroth layer is just the input and the Lth layer is the output layer, and each containing N0 up to NL neurons with a Lipschitz twice differentiable nonlinearity activation function sigma with bounded second derivative. So this is just saying that the activation function is kind of smooth. And the paper, and here we introduce the neural network realization function FL. So this maps this is a mapping from the parameter space RP to the function space F. And for a fixed distribution P in on the input space Rn0, the function space F is defined as the mapping from Rn0 to Rnl. So this is just the mapping from the input to the output. And on this space, we consider the semi-norm defined as this here in terms of the bilinear form. So you just plug in two F's here, and you will obtain the semi-norm with respect to the distribution P in. Okay, so in this paper, the input distribution P in is just the empirical distribution. So the data set is finite, and the sum of the direct measure is the makes the input distribution P. And the network function, which is an element of the function space, is defined normally. I don't think we need to pay much attention here. Okay. So the training of an ANN consists in optimizing f theta in the function space f with respect to a functional cos c. And this cos c and this c just maps from the function space to the scalar. So it's just something like a regression or cross entropy loss here. And then we define something called a multi-dimensional kernel K, which takes in two vectors of shape Rn0 and maps to a matrix with dimension NL times NL. With this kernel, we can define a bilinear map on the function. So f is just a function. F is a function, G is a function, and the bilinear form is just the expectation of f x transpose k x x prime g x prime, the expectation of this term. And we say that the kernel is positive definite with respect to the semi-norm here. If for a function the semi-norm is larger than 0, it always indicates that the norm with respect to the kernel is larger than 0. So this is somewhat like a positive definite matrix, but it's just a positive definite kernel here. And we need to define the dual space of the functional space f to be f star, where each element in the dual space is just some kind of linear forms, mu, which takes in a function and outputs a scalar here. So we can define a mapping called phi k from the dual space of the function space f star to the function space f, mapping a dual element mu to the function f mu, and the mapping is defined here. And here, so in our setup, we have a finite data set, x1 all the way to xn. We can write the cos functional c, the derivative of the cos c at a specific point f0, which is just a specific, which is just the function initialized. And the functional derivative of the cos c with respect to f is defined here, and it's just a mapping that takes in so it's elements of f star, which means that it will take in a function here and output a scalar. So I think a good way to think about this is that if you take in the perturbation in f, which is also a function, which is also an element in the function space, this linear form will output a scalar, which indicates the change in c with respect to the perturbation in f. And then we can define the kernel gradient, which is not a scalar anymore, but a function, and it is defined as phi k over this expression of the functional derivative. And the specific formula is defined is as below. So after all of these notations, finally we come to the convergence analysis. This is an overview of the steps that I'm going to take you through. So the bottom is the base case for the proof. And after that, we are going to make the scenario a bit more complicated by analyzing the case on a linear parameterized model. And we will show that the linear parameterized model doing gradient descent in parameter space is just equivalent to the FT follows the kernel gradient descent with respect to K. But we will talk about this later. And similarly, we'll also show the equivalence here. So, the scenario for the linear parameterized model and the infinitely wide ANN can both go back to the base case. Okay, so here's the base case. In the base case, what we want to prove is that if the neurotangent kernel K is positive definite, and the FT, which we will introduce in a second, follows the kernel gradient descent with respect to the kernel K, and also the cost function, the functional cost C is convex and bounded from below, we can conclude that FT converges to global minimum as T goes to infinity. So how to do this? First, we define a time-dependent function FT, whose value means at each time point, specific time point, FT is just a function in the function space. If the FT, if we say FT follows the kernel gradient descent with respect to K, K is just a neurotangent kernel, then we can write the partial derivative of FT with respect to T as here. And with this term here, we can express the evolution of the cos C with respect to T, because remember that the functional cos C with respect to F is defined as this linear form here. So it needs to take in an expression of how the function perturbs. And our partial derivative of Ft with respect to T just describe how the function perturbs. So we just plug in this term here, and we will obtain this term here, the second term. And by definition of the norm with respect to the kernel, so the evolution of the cos C with respect to T is just the minus of the square of the norm of the dft with respect to the kernel K. If we say if K is positive definite, then C will always be decreasing. Why? Because this term will always be negative if K is positive definite, except that when the seminorm of dft equals to 0. So when the seminorm is equal to 0, then the term here is equal to 0. But in all other cases, C will always be decreasing. So if the if the functional cos C is convex and is bounded from below, Ft will finally converge to the global optimum as T goes to infinity. Okay, so that's all for the base case. And now we are going to discuss the case in a linear parameterized model. The only thing we need to show is that during the gradient descent in parameter space for the linear parameterized model is equivalent to doing the kernel gradient descent of, with respect to K in the function space. And then we can just go back to the base case we just showed. So we first approximate the kernel K with a randomly sampled with P randomly sampled functions from the function space f from any distribution. And the only construction here, restriction here is that the covariance of these functions should be given by the kernel K. And with this P randomly selected functions, we can define a random linear parameterization F linear. So you can see it takes in the parameter theta and outputs a function. And the way to do this is just a linear combination of the functions. And the partial derivatives of the parameterization are given by this equation here, which is quite obvious. Okay, so let's now think about doing the gradient descent in parameter space. So when we do the gradient descent in the parameter space, the parameters follow the following ODE. The theta pt, the partial derivative of the theta pt with respect to t is just the partial derivative of the function that is the composed function of the functional cost and the parameterization function here with respect to theta p. And by chain rule, we can simplify the term to this term here. And by definition, we will rewrite the term as this one. So as a result, the function f linear theta t evolves according to this is just the definition, right? Because we know f linear theta t is just a linear combination of the p randomly selected functions, and the only thing changed is the coefficient here. So the change in the f linear theta t can be expressed as this term here. And finally, we can simplify this to the kernel gradient with respect to the kernel k tilde, where this k tilde is a bit different from the kernel k, but you can see that the I primes entry in the output of the kernel is the empirical covariance here. And remind that for the corresponding element at the I primes position in K, it's the real covariance. So by the law of large numbers, when P goes to infinity, the K tilde will converge to K. So that enables us to go back to the base case where Ft follows kernel gradient descent with respect to K. Okay, so after the linear parameterized model, we will talk about the real life, not the real life case, but a case closer to real life, and is of course more complicated than the linear parameterized model. But the idea is still the same. We just need to show that the infinitely wide ANN doing gradient descent in parameter space is equivalent to Ft doing kernel gradient descent with respect to K in the function space. So similar to the linear parameterized model, we can also show that when we are doing gradient descent in the parameter space, it is equivalent to doing the kernel gradient descent in functional space. The only thing changed is the kernel here. So the kernel, as you can see, is defined as this equation, and it depends on the parameter theta now, which is saying that during initialization, because you initialize the model randomly, the kernel, the neurotangent kernel, might change across different seed runs or something like this. And also when you are training, because your network parameter theta is changing, then your your tangent kernel is also changing. So in order to go back to the base case, we will need to show that the kernel converges at initialization and keeps unchanged during the training process. This is when the theorem 1 and theorem 2 come into play. Okay, so here's the theorem 1, but before that, it's the proposition 1. So the proposition 1 is for a network of depth L at initialization with a Lipschitz nonlinearity sigma, and in the limits as every layer goes to infinitely wide, the output function of theta k for k equals to 1 to L tends to IID-centered Gaussian process of covariance sigma L. So this is just saying each output neuron just simulates a centered Gaussian process F with covariance sigma L. And we can see that sigma L is defined recursively here. And then let's come to the theorem 1. So with the same conditions, we can conclude that we can say that the neurotangent kernel theta L will converge in probability to a deterministic limiting kernel. So theta L will converge to this term here. The second term here is just the identity matrix, and the first term here, as you can see from the below, only depends on the number of layers in the networks, the selection of the activation functions, and also the variance of the parameters. So when we initialize the model, we always use the Gaussian to initialize the parameters. So the variance of the parameters will be fixed. And also, if you have a fixed network architecture, then this is saying that your neurotangent kernel theta L will always converge to the same kernel, no matter how you initialize that. Not how you initialize that, no matter how many times you initialize that. Okay, so theorem 2 is saying that under some kind of assumptions, we can say that the neurotangent kernel at each time step always converges to the neurotangent kernel as same as the one that the kernel converges to at the initialization. So in conclusion, theorem 1 is saying that the kernel converges at initialization, and theorem 2 is saying that the kernel keeps unchanged during the optimization process. Combining this, we are able to go back to the base case again, and then we can still use the base case to show the convergence. Okay, so that's all for the convergence analysis part. And now let's go to the other aspect of the NTK, which is the generalization analysis. And the paper conduct the analysis under the specific setting of least square regression problem. So given a goal function f star and input distribution p in, the least square regression cost is defined as this one here. And we can define a function. The key here is that we can define a function ft that do kernel gradient descent with respect to k as here. So if we define the function ft as here, then we can get the solution of this differential equation in as the equation here. So we will do something to this difference here to show the insight in generalization properties of the neural network. The pi here is just some kind of mapping that takes in function and output another function. So when we decompose the difference f star minus f0 along the eigenspaces of pi, the trajectory of the function ft can be written as this one. So we can easily see that for eigenspaces with larger eigenvalue, because there's a minus sign here, the convergence will be faster for the eigenspaces with larger eigenvalues. So this is saying that during the optimization, the eigenspaces with larger eigenvalues will always be optimized first. And this suggests the benefits of early stopping when we do training. And lastly, we can, because of the linearity of the map here, we can, and if we assume that f0 is initialized with a Gaussian distribution, then ft is always Gaussian across all the time sets t. So if we assume that the kernel is positive definite on the data, and when t goes to infinity, we can express f infinity as the term here. The term is just the solution to a kernel-ridge regression problem. So then the generalization properties of the network can be analyzed through the lens of kernel methods, which have well-known generalization bounds. Okay, so that's all for my presentation. Thank you.